uh, many years of research, and I try to something like to pack a presentation which is not too technical, but just giving an overview about the technology and sometimes doing also a benchmark with the typical production processes that we have in jewelry. Uh, the, just for better understanding the structure of the presentation, I will do an introduction talking shortly about the traditional production processes to do jewelry, and then an overview about 3D printing in metals, and then talking about the materials. I mean, which kind of precious metal we were testing, and see the possibility to print them, and then talking about the resolution, which is a very common question. How are the details if we print when we compare to casting? And also the thickness, which is the thinner thickness I can print. Then about geometries. Many people talk about that on 3D printing it's possible to do very crazy geometries, but I will go in much more deep details to talk about what is the complicated geometries that 3D printing can really afford. And then about the surface quality, that is always an issue. That means the porosity, so the density, the roughness, and as well the supports residual, which is a typical unwanted problems that we have on 3D printed parts. And then about the productivity, also doing a benchmark with casting. So how many pieces can we produce with a printer? And how fast is a printer? And then also talking about the sustainability, so the environmental impact of 3D printer compared to casting. And then a short gallery about the latest parts we were printing. So every one of you knows that jewelry is divided by two big families. The first is the casting parts. So we pour a molten metal into the mold, and this represents 70% of the worldwide production. So casting is the most common process used for producing jewelry. And then starting from sheets, wire, you can produce handmade jewelry, or you can do tubing, or you can do chains, or you can, starting from blanks, you can do machining. So this is the very traditional process to produce jewelry. And what about 3D printing? I have a very old animation, which I'm every year showing to the people to explain how it works. So it starts from a 3D design, which is sliced in many slices. The slice thickness is around from 10 to 50 microns. And then the data are sent to a printer, which is previously loaded with gold powder or platinum powder or whatever precious metal powder we want to print. And this is the example. So I'm faster than the video. And so to see what happened inside the chamber, there is a wiper system that is spreading the powder on the building platform that you see on your left. And on the building platform, which is going down every step at one slice thickness, which means 20 micron every step going down. And the laser is just following the data coming from the computer and melting the particles. And this process continues until all slices are scanned. We are in front of a totally melted structure, so the particles totally melts. They are not sintered. Many people love to talk about sintering just because we use powder, metal powder, which is the only common thing that we have with sintering, but we are in front of a complete melted structure. And this happened till the end. All, as I said, all the slices are scanned, and you have the parts done in that way. So the type of process is in the family of powder metallurgy process. There are many commercial acronyms like SLM, which stand for selective laser melting, SLS, which stand for selective laser sintering, and DMLS, which stand for direct metal laser sintering. The one I love more is selective laser melting because as I said, I don't like to talk about sintering. If the sintering process will be the one that 3D printers should give to our jewelry parts, we will never be happy about the density. So we are in front of total melted structure. The technology type is a layer by layer technology, and the tested precious metal by our company, but by all other companies involved on 3D metal printed, is all the four precious metals. So gold alloys, silver alloys, palladium alloys, and platinum alloys. Silver is one of the less sexy precious metal to be 3D printed. So it's not really one metal that makes sense today to be 3D printed because of its physical characteristic. It's not really loving very much the laser and absorbing the power from the laser. The printer producer, we have 4 printer producers that are very focused on jewelry. One is Realizer from Germany, second is EOS from Germany, third is not the ranking, it's just because I love to start from the one we use. The third is Concept Laser from Germany, and the fourth is Sysma from Germany, from Italy. And then we have another few, this 4 has a printer that has the proper size for jewelry. Then we have Phoenix System, that is part of 3D Systems Group, SLM Solution, Arkham, and Renishaw. These last 4, they are much more focused on aerospace, automotive. But I will say that we are in the land. So Germany is the land of 3D printing on metals because most of the company come from Germany. And it's also the company where all things started. About the powder producer, the most common for precious metal powder are 4. So Progold from Italy, Cookson Gold from UK, but UK, Germany. Then we have Lego Group from Italy, and then Hildebrand from, it's a Swiss-German company. These are the 5 metals that we are every day working with. So yellow gold 18 karat, red gold 18 karat, white gold 18 karat, platinum 950, and also titanium. That is giving some other opportunity I will talk with you in the presentation. So very often the people ask how I arrived today, and I think that I received more than 10 customers asking me about mechanical properties. How is the material after 3D printing? Because the people think that because it's 3D printed, it's behaving a different way compared to casting. I will say no. The hardness is very similar to the casting part. I will say that it's something like 5 to 10% higher, just due to the kind of structure that we have on 3D printed parts, and later on we will see. I also prepare a benchmark between casting and 3D printing, comparing the tensile strength and the elongation. So you see the black spots shows the difference between direct casting, traditional casting, and 3D direct metal printing. Let me open a parenthesis about what the difference between traditional casting and direct casting. Traditional is the one where we produce the patterns injecting wax into the rubber mold, and this we call traditional one. And then there is direct casting, that is the one we 3D print the patterns in resin or wax, and then we assemble in the tree and go directly to casting. This is direct casting. And then 3D metal printing. So the tensile strength is something like 20% higher. And in case of elongation, it's something like 20% less. This is something normal in precious metal alloys, that when an alloy has much more strength, so we need much more force to break it, then the elongation is lower. But no one of you wants to reach the limit of elongation, because when you have a very high elongation, then you spoil your parts. And 33%, which is the typical elongation of this example, that is an 18 karat yellow gold, is much more than enough. Here we have the reason. The reason starts from the grain size. So the structure of every alloy is done by many crystals. In case of 3D printing, we have crystals which has a size always below 50 microns. While in case of casting, whether it's direct casting or traditional casting, we have a grain size that starts from 100 microns up to 2 millimeters. So this means that the alloy is even much more soft, but even much more, let me say, compact, dense. Another opportunity from material point of view that I wanted to focus here is platinum and titanium. Compared to other precious metals like gold, platinum, for example, loves very much the laser power. So its thermal conductivity and electrical conductivity is much lower than gold, and this means that it's absorbing a lot of the power that the laser is giving. So just to give you a very practical example, to melt, to scan, and to print platinum, we need 20% less energy, even if the melting range of platinum is something like double than gold. So that's why platinum loves very much gold. In case of titanium, it's opening a lot of opportunity also because of very high melting range, but very high, a big complication during casting. And is really, if we have to do a benchmark between casting and direct printing, and 3D printing, we can say that the easy material to cast are very difficult to print. And opposite, the difficult material to cast are very easy to print. So titanium is one of them. And then titanium is giving another opportunity, so the anodization, so the possibility to produce jewelry, and then doing a galvanic process. I mean, there is no deposition, an oxidation on the surface, and you can get many colors, and the colors depend from the layer thickness of the titanium oxide we have on the surface. And I will say that the thickness of that layer is typical like a rhodium plating that we have in jewelry, which is something like 200, 300, 400 nanometers. So it's something that also is very long-lasting. And then there is another alloy opportunity, something that you cannot cast, really cast. Sometimes element A is not a good friend of gold. They do not like each other. So one of the chances offered by powder metallurgy is the composite alloy. Now we are just in the early beginning, but tomorrow we can really put together things that they don't want to stay together. I will give the example of gold titanium or gold niobium. So gold titanium, if you put into a crucible gold and titanium, you do nothing. You are not able to melt them together. But in case you 3D print, you just entrap titanium particles on gold matrix, and is able to give you a very nice white color with a yellow index very low, below 15, in the range of 10. And if you compare with a typical 18 karat white gold palladium with 13% of palladium that has a yellow index in the range of 18, and then rhodium has a yellow index around 5 to 6, then we are really in a much wider condition. And then the density. Imagine titanium is very light material. It has a density 4 times less than gold. So the same ring has a weight 4 times less. So if we use that element to do a gold alloy, then it's much lighter, something like 30% lighter. And this, I don't want that it it sounds like cheap, because it's light, because it's cheaper. No, let's watch from the side that is much more wearable. So here we have the two rings that we were printing. The left one is titanium and gold, and the right one is gold and niobium. Things are still in R&D, but what I want to say is there is an opportunity that up to now, with the traditional processes, we were not able to take. So now we can take this advantage. About the resolution, now you could forgive me if I was not really following some standards, but if someone say, which is the resolution of the printer? If we count how many dots per inch we are able to make on a 3D printer in metals, the resolution of 18 karat yellow gold is 120 on XY plane surface. It means, in practice, that we can print the tails up to 0.15 to 0.2 millimeter. If we have something smaller, we cannot print. But in casting, I'm not really sure we are able to go down to this. We used to confuse the resolution with roughness, and this is very common. Then in case of platinum, you see that we have a much higher resolution on XY under 70 because it's absorbing very well the power, and the melting trace is much thinner. It's like to have a pencil, and when you draw with a pencil, then if you have a thick pencil, you are not able to do the same details that if you use a thin pencil. And platinum has a much thinner, is like a much thinner pencil. On Z-axis, we have a very high resolution that is up to 1200 because every layer is 20 micron. So here you can see also the kind of resolution in one ring that is possible with 3D printing to achieve. There is another thing to talk about. The thickness. People ask, which is the thickness I can do with 3D printing? So I wanted to make a benchmark between 3D printing and casting. So if we compare the brown line is the traditional casting. So the thinner thickness you can cast is 0.4 if you're lucky and you're able to inject the wax. But then when the surface comes bigger, so on the X-axis you see the surface dimension, bigger is the surface and thicker must be the thickness. In case of direct casting, because we are able to 3D print the patterns, we are able also to cast something much thinner, but then at the end, when the surface increases, then we have to increase the thickness. What is the wonderful thing is that on 3D printing, we can go down to 0.2 millimeter, which is that resolution, but it's constant. Whatever is the surface size, because there is no connection. We have not to fulfill with a liquid metal a mold. We have just to print layer by layer something, to grow layer by layer. About geometries, there is something very common that happens in jewelry. So in jewelry we have two kinds of possibility, or solid jewelry or hollow jewelry. The solid one you do by casting, for example, the teeny hollow you do by stamping or you do by electroforming. But if you want to do something in between, not possible. You can do by casting. On the top example, you do by casting in two parts, and I'm talking about a closed geometry, not with hole from through, and the hole need for the investment to fulfill the patterns. A closed geometry. So if you want to do, you do in two parts, and then you're assembling and you do soldering. In case of 3D printing, you have a monolithic part that is growing. So what is something that the people who produce high-end jewelry doesn't like very much is the soldering line. And the soldering line is something, for example, in red gold. It's it's always a nightmare. Because you have the line, whether for the color or for the mechanical properties that you have on the solder. Because when you go to grinding and polishing, it's always not resistant like the rest of the object. So you have the soldering line. But if you have a monolithic surface object, then you have not any more that problems. And this is another advantage. I have only this example. It's not realistic, but I hope you are able to understand my meaning. Hollow wearable and smart hollow with a constant size. So on the top, what we want to say is you have a volume, a solid volume, and from its weight you can reduce 80% of its weight, just changing the thickness. So not to looking for to have a very cheap parts. Image an earring, or image a very heavy ring, 50 gram. 50 gram maybe is too much, you want it down to 40 to 30. And then the second one on the bottom, the constant weight. So every one of you knows one thing. You go to the shop, you buy a ring, and the ring price is what? So 3,000 euros. But every one of you knows that the size 48 and the size 60, they are different in volume. But we do not sell by weight, and maybe the weight difference is 30%. So the quantity of gold that you put in there is much more. And what is possible to do with 3D printing is to have the apparent volume that is changing, but the real volume that keeps constant. I have a very nice story of a friend of mine. He says, if I go to the restaurant and I order double portion of food, they charge me double. If I buy a pair of blue jeans, and he was so angry, he said, oh, my size is M, but my friend is XXXXL, and the price is the same. For what reason? There is double material. So we cannot do that things, but why with gold? If a very teeny lady is going to buy a very small ring, pay the same money that a very different lady is going to buy that ring with a very big size. We are talking about gold. So this is one issue. Another issue is a designer has to anymore think about changing the design of the things that he wants to produce, because he has to reduce the weight. He can reduce and hide what is reducing. This is an opportunity affordable only with 3D printing today, or casting in 2, 3, 4 parts and then assembling. But this is not really the solution. It was the solution. And then there is the reinforcement rib. I don't know if the word rib that works, and please forgive me. What I want to say is a system, and the rib is that on the top you make something like a mechanical trick on internal geometry, just to reinforce the shape and to avoid any damage when you hit something. So you have a hollow parts, but still resistant. Or you put a very lattice structure in it, something like a system of the one that you see here. You see? So you make it hollow, but you put a structure that is enforcing inside the jewel. So this is another advantage, to make the ring at the proper weight. I don't want to say less weight. I just want to say the weight that the designer wants, because the designer knows which should be the proper weight of his ring. The surface quality is another issue, the roughness. So in this graph, I try to make it less complicated possible. On the left Y axis, we have the slope angle. What does it mean? The angle that the surface has against the building platform. So when you print something flat on the top of a cube, for example, Then the roughness of 3D printing, that is represented by a red line, is very high. Is around 60 micron. What does it mean? That every mountain, every peak on the surface is 60 micron, and you have to remove that amount of metals. In case of traditional casting, it's very low, it's around 15. And direct casting is around 35. But when you increase the angle, then 3D printing starts to get an advantage. So I will say that talking about the roughness, there is no story between 3D printing and traditional casting, because traditional casting is always much more smooth. But if we compare with direct casting, I will say that it's similar. Except we cannot call direct casting the casting produced using, for example, a solid scape wax, which is very smooth, because it's not direct printing. You produce a masterpiece there. Direct printing is like when you use a 3D system printer that you are able to print 100 pieces, 200 pieces, and then go to casting. That roughness is comparable to 3D printing in metal. The density, this is another issue. Because of the way that solidify a metal in casting and the way that we melt and solidify a metal on 3D printing layer by layer. So we repair any possible shrinkage that happens. We were doing a lot of investigation, and in case of casting, you reach a maximum density of 99.9%. What does it mean? There is 0.1% of holes, porosity, something that is unwanted in case of casting, especially if we are talking not about company that watch ring in that way. Oh, that is good. No, they take a loop and you watch how high end is required. In case of and this is the surface, so you can have some dots like this, but in case of 3D printing, you are able to achieve 99.99%. Don't want to say this, there are some weaknesses on 3D printing for sure, but I want to say that there are many advantages. This is one strength of 3D printing. This is something that we don't like in 3D printing. That is the support. So on the top image, you see a different support that are used for 3D printing. So there is block, volume support, so different strategy to hold the pieces on the building platform and to transfer the heat that happens during the melting, and then that heat needs to be transferred. So the kind of surface that you have when you cut the support is that one, which is comparable to the one when you cut the sprue, you cut the ingate, then you have to reshape that parts. Okay? Here we have many small in a bigger area. In case of casting, you have one big in a smaller area. On the left side, you see a surface of a ring where we were putting a very dense amount of supports. On the right side, where we reduce the amount of supports. Then the decision how many supports to put is something that is connected to the geometries, to the heat transfer, to the number of pieces on the platform, to the kind of material, and so on. Higher is the thermal conductivity, and lower is the number of support, and opposite. The production lead time. How? So when is convenient to produce by 3D printing? In case you want to make a benchmark between casting and 3D printing, to print something that is possible to cast that usually makes no sense. So for what reason? You should take a flight to go from here to downtown Munich. No reason. Okay, you go by walk or you go by train, but you can go by airplane, right? So if you want, maybe you take your own airplane, you go, but make no sense. So make no sense also in a production lead time to compare 3D printing and casting. But in case you are looking for, how long should I wait to get one item, 10 item, or 100 items. So in case of traditional casting, you have to, starting from zero, you have to produce the masterpiece, you have to make the rubber, you have to inject the patterns, you have to build the tree, 15 hours to burn out the flask, and then the day after you can do. Altogether, it takes something like 30 hours. We have not to count that we already have everything, because this is making no sense. In case of direct casting, it is much lower because you have not the time to produce the master, you have just to print. So we were doing that kind of calculation, and we can say that up to 10 pieces, 15 pieces, if you need something fast, 3D printing is faster than traditional casting or direct casting. 3D printing, if you have the printer in-house, in 2 hours you have a ring. If this makes sense for you, then it's faster. Then if you have time to wait, never mind. Then when you go up to 100 pieces, 3D printing make no sense in case the parts can be produced by casting. In case of part can be produced just by 3D printing, there is no benchmark, so you have to produce and finito, we say. The production capacity, just to give you an idea, here, maybe later if you want, you ask me how we did this calculation, but in case of casting, we were thinking about one wax injector, one casting machine, one embedding machine, one burnout furnace, and one casting machine. In case of 3D printing, we were considering one printer. So how many kilos a day you are able to cast with a very typical 15 flask burnout furnace, because this is the bottleneck of the process. I mean, the casting machine can cast a lot, but then you need to have many burnout. But we didn't make that kind of benchmark. In case of 3D direct metal printing, maximum you can print around 350 grams of jewelry per day. The day of casting is 8 hours. It's one shift. The day of 3D printing is like a turtle walking this way, 24 hours, 7 days a week. Then we were often talking about the sustainability. So the environmental impact of 3D printing. It's by filling, you see, oh, we have no investment, we have no wax, we have less electricity involved, so it should be less environmental impact, much more green, much more environmental friendly. And we were doing a calculation. So you see here, few things. So the red line shows a typical production capacity of a 3D printer, which is around 15 grams per hour. So it means that the quantity of equivalent CO2 produced is around 15 kilo per kilo of jewelry produced. But in case of casting, if you use on the x-axis, you have the process yield. So how many people in casting fulfill their burnout furnace every day? No one. I mean, only big and very structured company. But a small gold producer, they have a 20 flask burnout furnace, they put 3, 5. They always have a equipment much bigger than the quantity they need to produce. So if you run a burnout cycle only for 5 flasks for 25% of its capacity, then we have to talk about the process yield around 50%. So I will say that really it's not zero impact, but it's less than casting. And one more thing, we did not consider the investment. We have to take care to this waste, but we don't know which is the value or which is the known value of the environmental impact. We just consider how much CO2 we produce to bring the investment from the company to the place where you have to I don't know the word, never mind. But we don't know. Okay, that investment is there. What we do with that investment is something like a waste. To recover, to make this becoming something different. How much CO2 we should produce. So down to the gallery. So one typical structure that is nice to build with 3D printing is this one. So it's a kind of lattice structure, and this is something that is not possible to do with any other production process. You like? Good. You don't like? Okay, we go to the next one. But this is something possible to do. You ask me how to polish. No, you have not to polish. Or you like it that way, or you like it that way. Something that you can do with titanium. You can build the things already connected. Okay, so you have not to solder. It's not really nice, this, but in titanium maybe it's tough to think about soldering, and maybe it makes sense to consider. Another example here. This I love. This picture I love because now you have to tell me if it's nice or not. It's platinum 950. But look at the details. In my opinion, is amazing. So it's so smooth. And this is not treated. It's how it comes from the 3D printers. If we should compare with a cast part, I'm sure that we are not so far. So the meaning is, give me a question. Is the technology ready for production? It's just a decision. The technology is ready. Then we have to decide to stop using fax or keep using fax. That is a decision. But still many people use. This is a yellow gold 18 karat. And this is a typical roughness that we have on the surface. In this red gold 18 karat, we just show how it is a ring inside if we hollow. And this is the last. It's already linked. It's a platinum bangle. So, my presentation ended. If you want to have much more information, just visit us at our booth that is just there. And if you have any question, I will be very happy to answer. Thank you very much.
Thank you, Mr. Zito. Thank you for your insight into direct metal printing. Are there any questions from our audience?
Yeah, sure.